So this has been a perfect lead-in to Nick Henke's talk. He's going to be talking about Lustre ping scaling, which I think is what Dave was alluding to only moments ago. Ladies and gentlemen, Nick Henke.
Good morning. We're going to do a little talking this morning. I really want to thank Eric and Dave for setting me up with an hour. I haven't had an opening act in a while, so. This morning, we'll talk a little bit about the fine-grained routing configurations. Dave did a pretty good job of setting them up, so we'll kind of blip right over that. And dig in kind of the meat of the problem, where we've kind of discovered a problem at scale with LNET routing, and that's kind of this dead time issue. A little bit about the data collection and analysis that we needed to do, some of the tuning steps we've done, and then kind of some of our conclusions discussions, kind of figure out where we go from here. So the way we've been using fine-grained routing is in a small group, so kind of a slice between what Dave called projected and what he did with their 32 groups where you're just talking off of a line port. The reason we're doing this is to balance out bandwidth and also get some of the resiliency back and help localize traffic within the torus and take care of some of those issues. If you really want to know more, Dave's paper from TUG 2011 was a really good start, and I think that's where folks should start with that. So IOR and the dead time. Here is a nice, horrible graph. This is an instrumented IOR that we've run in production, and what we're doing is gathering per second timestamps to kind of figure out why we're not achieving full bandwidth out of a storage subsystem. There's a few things that are interesting about the graph. The tail off, I think, was more product of running in production, but the periodic, the dips we're seeing where the write bandwidth completely stops, and we're seeing that in this graph. The x-axis is quarter-second intervals. So we're seeing that in this graph about every 25 seconds. Long story short, since this is only a 20-minute talk, this turns out to be the Lustre pinger. The Lustre default timer is about 100 seconds, and the ping interval is a quarter of that. So that's kind of where we get our 25-second interval from this graph. Without jumping too much into the analysis, touched a little bit on the instrumented IOR. This we thought kind of needed to do to dig into the nature of the problem. There isn't a lot of good statistical data that comes out of Lustre, out of the application space, that kind of lets us see more than just a number coming out of some of these benchmarks. We did throw Collectl on the back end as we enhanced it for LNET data, as well as some per OSS data. It was a really nice, quick framework to gather data. And then with being able to pipe it into ganglion graphite, we can visualize that pretty quickly and start to drill down on problem areas and compare different metrics and Q depths to start seeing where things look a little hinky. I will notice that we'll note that the LNET data is not all that helpful, especially in the LND space. There is kind of no standard for an LND exporting data, especially Q depths, wait times, and on the router there's no directional information, so the only thing you really get is did it route a packet and how big was that packet. So it's kind of one of the challenges, and it's why I'm going to guess a little bit at some of the data. We haven't enhanced too much of the router data yet to give us a detailed view, but I think we got a good enough view of the data. So the pinger, it hurts. What we're seeing is usually a 3 to 8 second dead time. I/O usually completely stops or at least degrades very significantly. That 3 to 8 seconds for Cray turns into a 4 to 11% reduction in throughput. We do tune up the Lustre base timeout to about 300 seconds, which gives us a ping interval about 75 seconds. We have seen some spikes in this dead time to over 10 seconds, which gets a little painful. The ping messages are instantaneous loading, modulo about a second or so. They have been aligned for OS jitter and noise so that this data kind of shows up and doesn't trickle out the compute nodes and kind of interfere with MPI barriers and that sort of thing. Kind of give you an idea of how this math plays out at the low petascale, and I think kind of where we're looking this going forward, towards exascale. Right now, today, we're looking at about 25,000 clients on a high-end machine. 4 OSTs per OSS seems to be, relative standard. For a decent-sized system, this ends up being 360 OSS nodes. And if you do the math with the LNET pinger, it's every client pinging every OST. And that generates an instantaneous loading of 36 million pings, and those happen over a 75-second interval. With the fine-grained routing setup we're using, where we have 4 routers talking to 3 OSS nodes, we end up with about 75,000 pings per router node and about 100,000 pings per OSS, which kind of puts the math back into scale. It's not a horrendous load, but it is still enough to impact us quite severely. Fine-grained routing does make this a little tougher on us because each router node has fewer destinations that it can talk to. And with the way LNET has been structured in the LNDs, is the per-peer traffic is a bit of a bottleneck. And the amusing part about this traffic is there's not a lot of value in the traffic. Most of the times, the clients are sending this data because they aren't doing I/O to a target, which means they most likely don't even have a lock that would be evicted if they died, which is kind of why the OSS is looking for this data. The async journal feature kind of complicates this a bit because the return path is used to send back the last committed field, which allows the clients to flush their cache and kind of drop some locks and let them know that while the OSS has previously said they've seen the data, now the data is actually committed and out on persistent storage. Jumping kind of into a set of graphs that kind of narrowed in on one of these little ping intervals for us. We're looking at about a 7-second graph here. So the timestamps we're seeing are every 1 second. So there is a little jitter in the data since we're looking at it so fine-grained. On the left side of the graph, you've got the ping rate for a single OSS. On the right side, you've got the megabytes per second for a write. And it's a pretty clean instance of where the I/O traffic completely ceases, or nearly so, as we see the pings come in. The interesting thing is the pings don't just all arrive at once. So we kind of got a couple of questions. Why are the writes slowing down? And why are the pings not showing up more grouped together? If we look at the LNET receive rate for that same OSS, it looks very similar to the ping rate, right? So there's not a lot of difference in the rate at which LNET is telling us it receives a packet to when the OSS is actually processing the ping and recording that traffic. One thing to note is LNET won't actually receive a packet on the OSS node until there's actually a service buffer out of the portal RPC layer ready for the message to be delivered into. If we then take that further question and kind of look at why the writes aren't getting through to the OSS, the next thing you usually look at is kind of the service wait times. If the traffic was fighting on the OSS node itself, you would expect to see a big spike in the OSS queue wait time as those messages kind of collected up and weren't getting processed as fast. But we just don't see that. And what we do see is kind of this interesting double hump from the ping data, which lends us to some thinking that there's a bit of a blip as the initial buffer pool for the portal RPC threads are exhausted, and it takes a one interval for those to get reallocated and get the LNET traffic back flowing through it. So with no fighting on the OSS, we need to take a look at the router nodes. There are about 4 different queues on the LNET router, each kind of doing their own little bit of flow control. On the inbound side from our Gemini network, there's the peer router buffer. And this controls how many messages each node can route through the router and limit how many resources it can consume and kind of limit the damage if you get compute node death. Ballpark, we're running with about 16 credits per peer. And this graph is showing us how many messages are used in total on those peer router buffers. And we get kind of an instantaneous loading of about 30,000, and it kind of slowly increases from there for a couple of seconds and then drops off. So what this is telling us is the data is getting to the router node and is getting to the router node at about 30,000 messages a second faster than the router node's able to eject out the other side. And they're queuing up on the per peer buffers, which the other buffer that's on the ingest side of the router node is the router buffers themselves. And these are the landing zones that the router uses to move messages from one side of the network to the other. And in this graph, we're seeing about 3,000 router buffers used per second. And for the small messages, that's about it's a 4K page. And I think the router pinger messages are about 192 bytes. So we're seeing about 12 meg or about 12,000 pages total across the 4 routers. Take these two graphs kind of combined, and what the takeaway for us was that the data is getting to the router nodes, and depending on what size machine we're running this on, it either queues up on the peer router buffers or in the actual router buffers themselves. It takes, when you're configured for our router nodes, we're doing about 16K router buffers. So you need to get about 1,000 nodes before you'll start queuing in the router buffers. So this data is from about an 800 node machine. If we look then at the outbound side of the router and try to figure out where the messages are going or not, we can look at how many messages are queued per peer on the outbound side. And we're seeing something very similar to the router buffers, where it's about 3,000 messages every second are added to that queue until the backlog kind of clears itself. So it's a fairly simple look, but our take was that the per peer InfiniBand links on the outbound side of the router were really where the queuing was happening. Some of the tuning you can do to kind of help that per peer link revolves around the InfiniBand LND. It is a bit challenging to get this tuning right. The base ones are peer credits and concurrent sends. You have a limit of 63 concurrent sends with kind of default InfiniBand parameter, or the default LND parameters, based on the size of the queue pair that can be allocated. And the way it does it is it allocates a full minimum message size per concurrent send. Long story short, is you can crank up peer credits to about 126 in that scenario. You can get to 255, but that's the maximum in the wire structure. But to go from 126 to 255, you've got to start playing with some more esoteric features like map on demand, FMR pools, and things that have implications for RDMA performance that we really didn't want to chew off just yet. There are some other tuning steps we've taken, small router buffers, peer router buffer credits on the InfiniBand side, so that when the replies come back in, there's at least enough queuing space on the router itself. And just kind of a brief note that there's a bunch of other things that end up being a little twitchy for the configuration. Timeouts keep alive. Isaac touched on asymmetric router failure and peer health, which kind of go hand in hand. And then for the InfiniBand LND, there's an NTX and credits that we end up tweaking. None of this is really great for fine-grained routing. We have so few destinations that we're really relying on a per-peer connection and trying to saturate it with small messages. And the InfiniBand LND just isn't set up to do a small message saturation. If we think about things that Eric brought up in the exascale kind of notes, we're looking at about 100,000 messages across a 3-second window trying to get through an InfiniBand link. And we're having really, in this configuration, which is very tough for us to get that message rate through. To think about the million, the 10 million would be pretty challenging. And with current Lustre locking on the LNET code, there's a rough limitation of about 100,000 messages per second before you hit the single global lock limitations. So we have seen significant improvement by using peer credits. We can reduce that dead time from 10 plus seconds down to the 3 to 5 second range, but we've just run out of runway for tuning. So conclusions. LNET routing is not very friendly to small messages, especially trying to saturate small number of links with small messages. I think it's a combination of both LNET and the LND layers need to work better together to kind of improve this message flow. And I think it's going to be kind of important for us to get this right. Especially we think for metadata loads, extreme metadata loads, exascale, any sort of small file I/O, especially under 4K, because it hits that small router buffer. And what's a little concerning with that is there's actually 3, maybe 4 memory copies in the whole path, because these small router buffers don't do a store and forward. It's a copy in, a copy out, and then it's another copy on the server side to deliver the message into the Lustre stack. So there may be some room, some low-hanging fruit we can go with there. And with that, we'll jump into any questions or comments. Man in the purple jacket.
Does the gap go away when you don't have routers?
Does the gap go away when you have routers? There is still the buffer sizing issue on the OSSs. So,
Right, sure.
So I think you would still see kind of a blip there with queuing, but it is a lot easier in that regard, right?
When you were talking, there's 2 things occur to me. Number one, is that the router is being pathological, and number 2, in order to get the RDMAs to come in, you've got the little message that goes out to say, give me the data now.
Yeah.
Has to compete with everything else going on through the router, I guess. So
Yeah.
it'd be interesting to know which particular messages are being blocked.
Yeah, we hadn't looked at that too much. Well, I mean, the one amusing thing is the first thought we had when we saw this was, well, we probably shouldn't put metadata traffic through the OSS routers. At least do a coarse-grained segregation so that you can protect, LS from having 10-second return times when there's just kind of a nominal idle system. Yeah.
Is part of the problem that the clients are all doing the ping at the same time?
Yes.
Why don't, so is that based on some, because they all start exactly 25 seconds after they first mount? It actually ends up being about that because it's 25 seconds after they've done their last I/O to the target. So if you added a 1-second random timer, around this, and so that over a half hour, everything would be completely random.
For small numbers of nodes, yeah. But once you get into 20,000, you end up with pretty good aliasing. The other thing is
20,000 all at once is a lot worse than 20,000 spread over 25 seconds.
Yeah. We've actually tried to do that, but the pinger code is really aggressive about aligning the pings on the ping interval boundaries for OS jitter and noise, right? So if you have a constant trickle out of a node of these messages and threads waking up, it's going to really throw off your barrier times for large-scale applications. So it's kind of a chicken and egg. There's a Bugzilla number 12471, which I think we opened 5 years ago, about that time frame. I think we were still doing catamount and liblustre when we found this problem. So there's been some recent discussion there where we can actually just start pulling these ping messages out, especially if they're not, if the client doesn't have a lock open and doesn't have any asynchronous journal outstanding transactions, just get rid of the ping altogether.
I guess I'm just saying, if you mounted the 20,000 nodes instead of all at once, a second apart, spread it over the 25-second interval, it seems that would spread close.
It would, but you'd sacrifice your application performance because the ping on each node would happen at a different time. So if you've got 10,000 nodes all trying to do an MPI barrier with interrupts coming at random spikes in there, those barriers are going to get offset from each other, and the timing gets pretty exponential on that, and you end up with really long MPI barrier times because those ping intervals happen during the barrier and kind of throw off the app.
Okay. Oh, no, sorry.
One more.
So I would like to let you know, and I guess I was discussing the staging and test at Openshot, but it seems the ping necessity is going away rapidly for systems like what you deployed Cray, because the ping purpose is 2 ways. One is you detect the dead clients. That you can already do. You have your own house network source where you can let the service know that, hey, this client is dead. So this part we don't already need. The other part, which is when the clients need to be notified that the server is dead and they need to switch. That part is being implemented with integrated recovery. That's already part of it. So I would rather you to play with disabled pings altogether, or like, unless there's uncommunicated messages left that you need to clear away. But I think that would have a much bigger impact.
Yeah, yeah. And the interesting part is now that we're moving into kind of the routed frontier, is we lose the ability to play games like, say, inside the Cray, where we've got a health network and kind of use that information for evil, as it were. So it's the information is there, but since we're in a routed configuration, we can't export it out to the servers, at least not yet.
Right. Let's give Nick a hand.